Hi, my name is Klas Leino, and I'll be presenting the paper Stolen Memories about white box membership inference. And this work was done with Matt Fredrikson. So let me just start real quickly by defining what we mean by membership inference. The basic idea is that an adversary is going to try to predict whether a given point was part of a target model's training set. Now, while the adversary will obviously not have access to any of the target model's training data, they will have the following: access to some auxiliary data that's different from the target model's training data, but distributed similarly. They'll be given an even prior over members and non-members, and they'll have access to the training algorithm used to produce the target model. So the reason we care about membership inference is, first, membership itself may be sensitive. For example, I may not want somebody to know I contributed to a particular data set or study, but it also serves as a practical measure of information leakage in general, which may be able to be leveraged by a different adversary performing a different attack. And finally, it's directly related to differential privacy, which makes membership inference interesting to study from the point of view of defenses. So membership inference has actually been studied a lot in prior work, and most approaches fit under the black box threat model, where the adversary only has oracle access to the target model's outputs. But there's also been a little bit of work on white box attacks, where the adversary has access to the target model's learned parameters. The problem we have with this work is that it requires a sort of non-standard threat model where an adversary also gets to see a portion of the target model's actual training data. So the question is, it seems like there's more information available that the adversary could use to do better with white box access, even without access to the training data. Basically, can we actually leverage this to make a better attack? And of course, I'm sure you guessed I wouldn't be in front of you presenting today if the answer wasn't yes, we can. So in our work, we show how to explicitly identify memorization in deep networks and how to weaponize it for membership inference. Moreover, we find that our white box attacks can be more readily calibrated to increase the attacker's confidence in positive inferences. And we also test our attack against some popular defenses to try to get a better understanding of their practicality. And I'll be pointing out some interesting results there about differential privacy. So now we've sort of laid the groundwork for membership inference, I'm going to take you through some of the key insights from the paper. So first, we provide a more fundamental understanding of how overfitting actually manifests itself in a deep network. And then I'll show how to use this to make a new type of membership inference attack. And finally, I'll highlight some of our key results and some interesting findings on defenses. So the key intuition we use for developing our attack is that a model provides evidence of membership through the sometimes strange way it uses features. So to just give a kind of cartoonish example, let's say we have two pictures of two celebrities, A and B, that we're trying to recognize. And you'll notice for both celebrities, they have sunglasses in 25% of their images. But let's say we sample a training set, and the way it works out is that celebrity A has sunglasses in 50% of their pictures, while celebrity B is more typical with sunglasses in 25% of their pictures. So now if we're going to train a model on this, the sunglasses are actually predictive for celebrity A since they show up more often for celebrity A than B. So we might expect that the model could encode this as a feature that it uses to predict celebrity A. So now when we pass an instance of celebrity A with sunglasses, the sunglasses feature would get activated and then used to produce the output A. And so the claim is that because the model used the sunglasses to predict celebrity A, we can maybe think that sunglasses are more common than average for celebrity A, sort of leaking that there are an unusual number of images of celebrity A with sunglasses in the training set. So if you saw a picture of celebrity A with sunglasses, we might think it's more likely to be in the training set. But so here's a slightly more realistic setting with an actual model and actual data. So these are some training points from the labeled faces in the wild data set. And we can see in the top right corner, there's a picture of Tony Blair with a distinctive pink black background. Now, if we take explanations on some typical test instances of Tony Blair, where we highlight the pixels that are most relevant in making the classification, we see that the model seems to focus on his face like we'd expect, although there's no pink background here. But on the training instance with the pink background, we actually see the explanations highlighting the background. So this is basically leaking the fact that there must be a training instance of Tony Blair with a pink background. So if we know that's rare, we might think this picture is more likely to be in the training set. So the basic idea is that features that are distributed differently in the training data from how they're distributed in the general population are going to provide evidence for membership. And this is going to be apparent by how the model uses features. So next, we're going to formalize this intuition and show how to use it to construct an attack. And we'll start with a simple case with linear models and then explain the key insights we use to make it work for deep networks. So let's say we have two distributions, eta star and eta hat, and they might look something like this. So now if we consider a point x prime, X prime is more likely to have been drawn from eta hat than from eta star if the probability according to eta star of getting X prime is less than the probability of getting X prime according to eta hat. So we can see here, for example, that there's a discrepancy. So X prime would be more likely to come from eta hat in this case. And so we can actually make a classifier that predicts whether X prime was drawn from eta star or eta hat by making a decision boundary wherever the orange curve is above the blue curve. So for this example, it would look like this. And so to turn this into an attack, we can think of eta star as the general population, or basically the non-members, and eta hat as the training set. And of course, an attack won't be able to know the means and variances of eta star or eta hat, or even if they're Gaussian. But the key idea is that the weights from the target model can capture some of the relevant information. So we can use this general idea to make an attack that's based on the weights of the model. And we'll look at that next. So the goal is we're going to sort of make a connection between the weights of the model and the training distribution. And we'll do that using some simplifying assumptions that let us actually analyze things. So we'll assume we have Gaussian naive Bayes data. We'll also assume that we can model the training set as a Gaussian distribution using its empirical mean and covariance. And finally, for now, we'll consider linear target models. And the key ideas are that first, using these assumptions, we can analytically derive the optimal attack from the means and covariances of the true and training distributions. But we can also analytically derive the optimal weights of a linear classifier from the mean and covariance of the training distribution. Basically, this is where SGD would converge. And so what we can do is combine these and substitute in the weights for the distribution parameters to come up with an attack that's only in terms of the observable parameters of the model. And basically, we can use this attack whether or not these assumptions are met, but under these assumptions, an attack would be provably optimal. So to summarize how our attack works, first we train a proxy model on the auxiliary data. Then we compare the weights of the proxy model to those of the target model to create an attack model. And basically, the attack model is going to place a lot of weight on the features that are used differently in the target model than in the proxy model. Basically, the features where the weights of the target model and the proxy model are really different. And those are going to be the features that are used to determine membership. So now we're going to show how to extend this to deep networks, since that's what we really care about. And we'll do this by thinking of applying the attack we just covered to an individual layer of a deep network. And what we do is we take what we call a slice of the network, which partitions it into two parts, H and G, where you can think of H as computing some features to work with, and G is classifying using those features. And the key important ideas are that first, the target model and the proxy model have to share the same internal representation. So they're basically working on the same computed features. And we think this is what's caused prior white box attacks to require access to some training data, because they're based on transferring an attack from a model trained on the auxiliary data. But there's no guarantee that the internal neurons in one model would represent the same features in another model, which is why they need some of the target model's real training data to make that connection. Then we also use local linear approximation at each point we're attacking to approximate the top of the network, G, as a linear model, so we can apply the attack described earlier. And there are some different ways of getting this approximation, which we discuss in the paper. But for now, you could think of one way as just a tangent line to the network. So if you have a function like this, the local linear approximation at point X would look like this. And notice that the linear approximation is different at every point, so we're not just replacing the whole network with a linear model. And just note that we can make an attack on each layer of the network and combine them to get an attack on the whole network at once, and the details for this are in the paper. And finally, I'd like to cover some of the key results from this work. We'll briefly look at the performance of our attack and also touch on some results we had regarding differential privacy as a defense against our attack. In terms of the performance of our attack, our results could be summarized as follows. So first, we perform better than black box attacks, both in terms of accuracy and in terms of precision, which is basically the confidence we have on positive inferences. And then we also have the ability to calibrate the attack for high precision. And basically, we argue that it's not so great to just, like, for example, label pretty much everything as members. But on the other hand, if you had even a few points where you could be really sure that you identified them as members, that would be a serious privacy concern. And we found that previous attacks aren't really well calibrated like this. And finally, we can get good precision even on models that generalize really well. Like, for example, MNIST has only 1% generalization error, so not much overfitting in the sort of normal sense. But we can get 75% precision on our positive inferences. And prior attacks really can't do much of anything on MNIST, since it doesn't really overfit much in terms of accuracy. And so I don't have time to go into details on differential privacy, but basically, if you train a model with epsilon differential privacy, then you get a guarantee that no adversary can achieve an accuracy greater than e to the epsilon over 2. And note that if epsilon is bigger than log 2, which is about 0.69, you actually don't really have any meaningful guarantee since accuracy is always less than 100%. So when we tried differential privacy as a defense against our attack, we found that, as expected, small epsilon reduces the attack accuracy, but it's really costly in terms of the actual model's accuracy. When epsilon is really small, the models were pretty much doing as well as random guessing. So what a lot of people would want to do is use a bigger epsilon to get a more useful model. And basically, you could imagine maybe you still get some privacy benefits from this in practice, even though the theoretical guarantee is not really there. But basically, what we found was a large epsilon sometimes works, but actually often the attack starts to do pretty much how it done without the defense when you make epsilon big. So for example, on labeled faces in the wild, when epsilon was raised to 16, which is actually something that would be used in practice, the privacy loss was pretty similar to with no defense. And actually, the other thing is, on most of the models where 16 did give a good defense, like on CFAR, the accuracy of the model with epsilon 16 was still bad. So a lot of the time it seems like you might start to lose benefits once you make epsilon big enough to get good accuracy. So this really suggests there should be more work on training differentially private models to overcome this trade-off. And in conclusion, I'll just go ahead and leave these key takeaways here. And of course, this is just a 12-minute talk, so check out the paper for details on the analysis, more sophisticated variants of the attack, additional experimental results, and evaluation of other defenses like regularization. Anyway, thanks so much for watching, and I look forward to your questions. Thanks.